All right, so I'm going to talk a little bit about the recent developments in GoFit, and I will be introducing our next two speakers as well. So first, I'd like to start with a special announcement. If you'd like to follow along with the talk that's following mine, you can open a terminal, as long as you have a Unix or a Mac machine, and run these two lines: pip install scikit build cmake. And then if you have a NVIDIA graphics card, I would recommend including this pip install options part of the next line, but if you don't have a NVIDIA graphics card, you can ignore it. And then you can just do pip install -v GoFit. This will install the two prerequisites for GoFit, and it will install GoFit for Python. So as long as you have Linux or Mac, a fairly recent version of your standard scientific Python tools like pip, numpy, and matplotlib, you should be fine. So if you just enter that or copy and paste it from the slides online, and you should be ready in about 10 minutes or so. You should be ready to run the commands that Himadri will be showing. So first, let's get into GoFit. What is GoFit? It's a package that's designed for highly parallel fitting. It's designed to look like and feel like RuFit, but to provide much higher performance. You should be able to get 100 to 1,000 times faster than single-core RuFit using a GPU, or even just utilizing a modern, highly multi-threaded CPU. GoFit itself was released in 2013. However, there has been quite a bit of development, especially recently, on it since then. GoFit 2.0 was released mid last year, and the 2.1 release occurred right before the end of the year. In fact, there is a 2.1.1 release today. So the main features of GoFit 2.0 I won't really go over. Now I'll just mention a few of them. There are some other talks, such as the talk at Fredrick 17 or ACAT 17 that are linked here on the slide, that go into those in much more detail. Most importantly, though, it made things much easier to build, much easier to use. Lots of features that were being developed in separate forks for different analyses were brought back into a single master branch. And that was sort of the focus of 2.0. There are some other features here which you'll hear a little bit more about that actually were part of 2.0 that have not received too much attention until now, such as the ability for it to run on multiple GPUs using MPI. So you'll hear a little bit more about that in the second talk. So let's talk a little bit about GoFit 2.1. 2.1, the main new feature in 2.1 is Python bindings. GoFit 2.0 had a very crude version of Python bindings that just included one PDF as a proof of concept. Well, 2.1 has bindings for all the PDFs and for just about anything you can do in C++ in your model composition. So I'm not going to say too much about it. You can see a little example of what the Python code looks like here. It's easier to read and write. It's very easy for you to script and to adjust and tweak your model, and you don't have to recompile every time you do it. You'll hear a lot more about this in the talk following this from Himadri. So I'm going to instead focus on a few of the features that made it into the C++ side. One of the features that obviously is related to the previous slide is the Python-like memory management. This means that variables now can keep track internally of the value that they're pointing at, and you can simply pass them around, use them as if they're a normal object or like a Python object, and they will not be destroyed until all the PDFs that use them have been destroyed. So it's much easier to set up your model. You don't have to do your own memory management, and it behaves just like Python. It also makes the Python bindings a lot easier to write. And this is a common cause for seg faults, for a variable being deleted while a PDF is still using it. Another change that affects the amplitude models, GoFit has 3-body and 4-body amplitude analysis models. And those have now been separated out into separate classes. So just taking a look at the right side of the screen here, which of those two PDFs on the top is a relativistic Bragg-Wiener and which one is less? Well, unless you happen to be looking at the source code of GoofIt or looking at something like that, you probably don't know. And in fact, if you don't know the types of these variables, you can't figure that out because the different PDFs are based on the order of the and types of the variables that you put in. So in the new version, you explicitly create a new PDF with a specific name, and this allows us to have a consistent signature each time because we're not relying on the order of that signature to figure out what you're trying to ask for, and it allows us to in the future optimize and remove if we have one of these that doesn't, for example, require one of these parameters or requires more parameters. It's easy for us to add that or remove that. So it's much more readable. I would say this is it's now much easier to code correctly, that is. GoofIt 2.1 continues the development on the build system. GoofIt 2.1 really does have a state-of-the-art CMake build system. If you're missing MinUI 2, it will now be built. Even if you have root but no MinUI 2, it will still it will just build the MinUI 2 and then use your existing root. So 2.0 you either had to have all or nothing, and in 2.1 you can actually work with a root that doesn't have MinUI 2 enabled because it's not actually a default option in root. The coding styles are enforced. There's quite a few of the new features in CMake, new versions of CMake are supported. In fact, it will even use some of the 3.10 features if you have version 3.10, which is the most recent version of CMake. But it will use things like CUDA native, the native CUDA as a language support that's become available in the latest versions. It's also the only package that I know of that can build on top of the Apple LLVM compiler and use OpenMP, because OpenMP is not supposedly supported in the default Apple LLVM compiler, but GoofIt can support it. So this means that you spend less time preparing and setting up GoofIt, and you get to spend more time on actually working on your models. It also makes it easier for a new user to contribute. These commands, if you have the basic prerequisites, are enough to install GoofIt. And if you go to this link, there are lots of explicit instructions for different platforms. So 2.2 is something that will be coming out probably in a few weeks. This has a completely redesigned PDF indexing. I'm going to save all the details for the third talk of today, but just to briefly mention what it's about. GoofIt is really in three parts. You have your PDFs, you have your composition of those PDFs, and all that's built on top of the core. Earlier versions of GoofIt have really focused on this composition step. The Python bindings focus on this composition step, making it really easy to put together models out of existing pieces. The PDF indexing will make PDFs themselves easier to write in C++, and will give us tools to improve the evaluation later. So in the future plans, GoofIt is still under development. One of the things that's being worked on and we would like your help working on is documentation. There's a very nice README. The API documentation is now being built on each release. But you can help us with either of those things, or you can help us with the GoofIt tutorial, which is a fairly empty site right now, but it's very, very easy for you to contribute. Just click on this Help Us link, and that will take you to the GitLab site, and then you can just click Edit on any page. And if you're learning GoofIt, maybe you can add some of the things you find out as you go. There are several analyses that are ongoing that are using GoofIt. The improvements that come about as part of these analyses will be rolled back into GoofIt. And if you're currently working on analysis, or you start working on analysis with GoofIt, if you find anything that is part of the core of GoofIt, for example, some improvements to plotting or something like that that you would like to add, please let us know. It's easy to contribute. Also, something else to keep in mind is the upcoming Hydra framework. It's a very, very promising framework for highly parallel scientific calculations. It supports a variety of different backends, and there are plans to eventually integrate or improve the interaction between the frameworks at some point. So feel free to go here and take a look at the Hydra framework. There's a new release of that coming out pretty soon, I believe. So, quick summary: GoFit is a really, really fast tool for fitting. It's become much easier to use. It now has Python bindings. If you're interested in developing a new analysis, it might be a perfect time to start trying out the Python bindings and to let us know how well that works. And GoFit 2.2 has even more features, and that's coming out soon. And we're available to help if you're interested in using it. So if you've been building GoFit at this point, it should be done. It should be very close to done or done. And you should be ready for Himadri's talk. This was a very recently released version of GoFit, so if there are any issues, please let us know and we'll see if we can fix them. All right, thanks. Any questions?
Thanks so much, Harry. Any questions from outside, maybe? Or comments? Of course, you probably get to meet with the second presentation.
Second and third, we'll go into more details. This is sort of an overview.
I'm wondering if I should ask here or later about the Python bindings, if input data sets can be any NumPy array.
You'll see some examples, but yes, I think the example I put in the slides even is a NumPy array. Yeah.
Okay. Okay.
Data from matrix. So anything that provides a buffer interface in Python can be given to the matrix from matrix, and there's also a toMatrix as well that lets you access the data again.
Well, a buffer and a data type, right?
Yes. Well, anything that provides the buffer class and the data type needs to be a double.
Mm-hmm. Oh, is it all doubles throughout?
There's a user configurable setting, but we've always used doubles.
Oh, okay. Okay. No, this is just new to me. That's all.
Anything pressing? Otherwise, we get to Himadri's more hands-on, and then hopefully there will be a bit more discussion as well. Okay. Yeah, it's okay. Thanks again, Henry. You want to go?
There it is.
Sorry, this
the little yellow tab right
this one.
there.
Okay.
This one is larger, so
Right.
the shape is different, so it's not going to scroll.
Yeah. Okay.
Right.
Since you know better the slides, I would even say that you can just proceed. Yeah.
Okay.
As matter.
I'm trying to figure out some way to actually get the whole slide on the page.
It's supposed to be one of those guys.
That one.
No. Or else, in terms of the percentage, it would be fit or something like that. Can you just give it a go?
Ah, that's right. Fit page. That's what I was.
Is it okay if I share my screen? It would be just easier to go over the slides.
We have it full screen now, so it doesn't harm. You can just say next slide. It's
Okay, sure. Okay.
Please go ahead.
All right. Thank you. Hello, everyone. My name is Himadri. I'm an undergraduate student at University of Cincinnati. I have been working with LHCb group. I have been working with LHCb group for the last 8 months, and I'll be talking about how to use GoFit with Python. So next slide, please. So if you have not opened your computer yet and installed GoFit, please do so. It's very easy setup, just 2 commands. First, we need scikit build cmake, and then we can just install GoFit. It should take 10 to 15 minutes in building everything, and then after that, we are ready to go. We can use GoFit like any other Python module. You can just by installing using pip install. So next slide, please. So how are we making GoFit available in Python is by building Python bindings. So basically we have all the C++ probability distribution functions, and we are binding it using PyBind11. It's a header-only library. It exposes all the C++ types in Python so that we can create bindings of it, so that when we are using these functions in Python, they are available. So there are other libraries too which can do the same, but we decided to go ahead with PyBind11 because of the earlier knowledge we had in it. So moving on, next slide, please. Where to start? So we install GoofIt, just one single line of code from GoofIt import asterisk. It will import all the modules available in GoofIt. So it's as simple as using any other module like NumPy, just import NumPy. In the same way from GoofIt import everything. Next slide, please. So here I will be taking through an example file. It is addition.py. What it does is it generates two probability distribution functions and then adds them using another PDF. So here I will be taking through the entire code. So in the beginning, we can see that it says from GoofIt import. So it's just importing GoofIt.
Hello, son. Could you please go back the slides? We were disconnected. We couldn't hear your file.
Disconnected, and you just came back now.
Okay, sure. Can you go back? Yeah, something happened. I think 11 people left the call just automatically.
Yeah, video dropped a very large number of people. And somehow you popped up in the middle as if you'd never been lost.
Interesting.
Mike, we left in page 4 or even before?
No, on the first page.
Wow, okay. There was a noise about that. Because for us, we didn't get any disconnection, so everything was smooth. We didn't see anything. Okay. Himadri,
okay.
Yeah, please.
So basically what I will be talking about how to use GoofIt in Python.
Did you introduce yourself?
Yes, I did. Okay, I didn't know that. I missed that part too. Okay, let me just go from the beginning. Yeah. Hello everyone. My name is Himadri Pandey. I'm an undergraduate student at University of Cincinnati. I have been working with LHCb since May 2017 at UC. And I will be talking about using GoofIt with Python. So next slide, please. Okay. If you have not installed GoofIt yet, please do so right now. Open your terminal, and you can use just two commands to install GoofIt. First is pip install scikit-build CMake. It will install CMake and scikit-build. And then the second one is pip install GoofIt. It will install GoofIt. So it's a very simple installation, like any other Python module. Should take around 10 to 15 minutes. So by the end of this talk, you should be able to actually create an example by yourself and use it. So moving on. Next slide, please. How are we using GoofIt in Python? So we have created Python bindings. We are creating Python bindings using PyBind11. PyBind11 is a library. It takes all the C++ types in Python and just exposes them so that they can be used in Python code. So it's very simple to set up. So if you are interested in setting up your own Python bindings using PyBind11, there's good documentation there, so you can do that. Apart from that, yes, so that's that. And next slide, please. Okay, so how to start, where to go? First thing we need to do is importing all the modules from GoofIt, and there's just one line of code from GoofIt import *. It will import all the modules available in GoofIt, everything. So it's as simple as importing any other Python module, for example, NumPy or matplotlib. Just import NumPy, import matplotlib. So as simple as that. Next slide, please. So over here, I will be taking through an example file, which is addition.py. What it does is it generates two PDFs, probability distribution functions, and adds them using another probability distribution function. So at the top, you can see in import, we are importing GoofIt, importing NumPy, and matplotlib. Moving on, the second line says print GoofIt info. It just prints some information about GoofIt, and there's a nice picture of GoofIt. So nice, fancy. Then moving on, we are generating data sets. So we have observable XVAR, and then we are creating an unbinned data set. So we have created an object in our computer memory, and then we are going to fill this object by using random variables. So you can see we are making a data set from 90% Gaussian and 10% flat data. So simply using NumPy, np.random.normal, and np.randomuniform, we are able to create this data set. And we are also creating a matrix so that we later we can give this to our Python bindings to create those PDFs. So moving on, please. And next slide. Okay, so here, first thing, we created two variables, xmean and xsigma, and then we are using Gaussian PDF, which takes XVAR, which we had already generated previously, xmean and xsigma, to generate a Gaussian probability distribution function. And after that, we created another variable, constant, and we are using constant and XVAR to create another PDF, polynomial PDF, generating another PDF. And now we have two PDFs. We want to add these two PDFs, and we can add these two PDFs using our add PDF, which is already there in GoofIt. So as we can see, it's very easy to generate any PDF. We just need to create variables, and we're generating PDFs and then adding them. Finally, we are fitting this data. So if you have been following me, you can copy the code from the presentation and paste it and run it, and you should get the results I will be talking about later. So next slide, please. Okay, so this is just the plotting part. So plotting is available in GoofIt 2.1.1, which was released almost an hour back. So there might be errors when we add this plotting part. We are not sure yet. So yes, if you get errors, please let us know and we'll help. So this is basically plotting our fits to see what the result will be. So next slide, please. So if the plotting works out, a plot like this should be generated, and there's more result which we will get even if the plotting doesn't work out. So next slide, please. So in any way, we should get results something like this. It says welcome to GoofIt, and all the information about fitting, how much the convergence was, how much time. Next. And something like this. So this should be the result we should be getting after running the code earlier in the presentation. Next slide, please. So what are some of the good features about GoofIt and what is available right now? So we have converted 9 out of 13 C++ examples in Python. So you can start using them right now. It's all available out there. And since we are talking about writing your own code in Python, there's so much support available from Python and PyBind 11 community. So if there's any error, they are also there to help, not on the GoofIt side, but on the Python development side, definitely. And on the GoofIt side, we are here. And talking about some of the features, why is it so great? Why should we use this Python aspect? So simple setup, easy to use. Python is an easy language, so doing anything is very easy. Then adding any Python functionalities is very trivial. So if you want to add something new, need new libraries, plotting anything, it's all out there. And as we create new Python bindings, it will be created in the future. We necessarily don't have to do anything on our side. As they are added to GoofIt, they would be accessible in the Python code. Next slide, please. So concluding everything, just set it up using 2 lines of code and 2 commands, and then use it using 1 line of code. As simple as that. Very simple to use. And yes. Next slide, please. Questions?
Thanks a lot, Himadri. Yeah, indeed.
Does anyone have any questions from video? Does anyone have any results potentially? Or bugs?
Yes.
And if you haven't tried this, just feel free to try this on your own at some point later. You can just do it inside a Docker container or a virtual environment or whatever you like. It'll respect whatever you, however you like to work. But feel free to just try it out and let us know if there's any issues.
My pip install inside a Docker container is still running because it crashed and failed a couple times. It might be useful to also just push out a Docker container as a post-release activity.
Yes, there is a Docker container for GoofIt, but it's going to be 2.1.0, not 2.1.1, because that came out today. I can try to update that though.
Yeah, because I mean, at least myself, I hate the potentially polluting a development environment. So I always lean towards doing a Docker container for something that I want to toy around with before I kind of install it in my base development host. Just
I do that as well. Oops, that's not what I wanted. Why is it Wikipedia? All right, somebody set the search to Wikipedia on this browser. There we go. No. Okay. So if you go to the GitHub page, you will find that there is a list of commands, and this is the actual Docker, the Docker commands. This is how you can set up in several different Docker containers. So like Ubuntu or CentOS, but there actually is a Docker container based on the root Docker container that's provided here, either for the OpenMP, or you can use an NVIDIA Docker. If you have NVIDIA Docker, you can do it with a GPU here as well. The version will be slightly old, so at the moment you would need to update it if you want to get to 2.1. One of the commands in that plotting screen was missing from 2.1.0. But this would be the Docker. This is a ready-to-go Docker container for that, with GoofIt already ready to run. Okay.
Anything else before we then move to the next presentation to be within the hour roughly? Yeah. Okay. Thanks again, Himadri.
Thank you.
There's this, but this is the PDF.
No.
Okay.
Can I share my desktop? Oh, you got it.
We have it. No, that's okay. Oh, not supposed to be that.
How do you get out of presenter view?
Yeah.
It thinks that that TV is doing the presentation.
And slideshow. Yeah, we're not supposed to be doing that. Okay. I think we're ready, Brad. We're sharing
Okay.
the screen. Yeah? Please go.
Well,
Okay, hello. My name is
doesn't
Brad
look
Hittle.
very full screen. Brad,
Well,
Yeah,
perhaps
I
you
think
could
you're sharing the wrong
desktop?
screen there.
Go ahead and share your desktop. Can we turn this off?
You don't have a full screen?
No, Eduardo.
It's full screen for the alternate presentation screen on PowerPoint. It looks
Okay. Okay, so if you share it, just escape it.
Got it, Brad. Thanks.
Yep. Hello, everyone. My name is Brad Hittle. I am a research software engineer at the Ohio Supercomputer Center. Just a disclaimer, I'm not an expert in high energy physics, but I do collaborate and I work on GoofIt part-time.
I guess.
So GoofIt, as has been mentioned, is a library for fitting probability density functions. The main interest is using GPUs for performance. And so what I'm going to talk about today is some of the modifications that I've made that involve adding multiple GPUs, memory improvements, and then the new indexing layout and how to write new PDFs using C++. For multiple GPUs, we used MPI. This feature is available in GoofIt 2.0. Each GPU gets a portion of the data. If you have one GPU per workstation and you have 4 workstations, you would take the whole data and divide it by 4. If you had 2 workstations and 2 GPUs each, you would divide the data set by 4. And here's a couple graphs to show you the performance. The left-hand side shows you, the left graph shows you a Dallas fit with a very small amount of events. And you'll see that the performance is pretty bad. So 2 nodes, 1 GPU, we barely get 1.5 times speed up. But if you look at the right-hand graph, we have a lot of events. We have 9 million events, 2 nodes, 1 GPU, and we end up with a factor of 2 times speed up. In addition to adding multiple GPUs, a lot of the PDFs use cache. So they'll save a value and they will use it later on in the calculations, and they don't want to recalculate it all the time. So I addressed some of the problems with the memory layout. The original structure was using an array of structs. So it's one big array, and you have a structure. In this case, it is 16 resonance values that are used per an event. And this memory layout isn't beneficial to use on a GPU. I changed this to a structure of arrays, so we have 16 different arrays, and each array is specific to a resonance, and then you would have each event's value, cached value, you would read from this value, read from this array. And with this, I achieved a 25% improvement using this Dallas with 9 million events from GoofIt 1 to this new memory layout, just changing the caching. In addition to this, so GPUs were meant for gaming, and they were meant for loading up textures. That's the main goal that a graphics card is for. It's for video games. They have a specific cache that they use when they're reading in these textures, but accessing that for scientific computing is difficult, mainly because when you try to use it with older versions, it would add in linear interpolation, and you don't want to change them. You don't want to change any of your values. And when the Kepler GPUs came out, they added an instruction that allowed you to use the caching without changing the values. And in this read-only cache, we use it for a variety of different things, but we can't use it for observables. It only works on global values. Whenever you're fetching memory from global memory is when you can use this read-only cache. And adding this feature in, I was able to get a 20% improvement on this Dallas example, and it worked for both a small amount of events and a large amount of events. And the last point in terms of memory organization that I want to talk about is indexing. So original GoofIT 2.1 indexing had a model where you would create a PDF, you add indices into this index buffer, and then you have a lookup into separate buffers using that index buffer. And
Brad, you're cutting a little bit. Is anybody here very smoothly, or it's cut for everybody?
Yeah, it's cutting for me too.
Yeah.
Cutting.
Maybe that everyone needs to mute.
Maybe you are too close.
is this any better?
For so far, yeah, but let's see.
Okay. Let me know if it starts cutting out again.
Okay, thanks.
With this, we have two memory lookups, and that's really slow. We need to reduce that the amount of memory lookups. The second issue is that when you add more and more PDFs, you have more random memory accesses because you're trying to pack the memory. You're not trying to use the memory sufficiently and lay it out. And what I want to show you now is just an internal representation of how two Gaussian PDFs look next to each other. So color coding these, the light blue on the left is the first Gaussian, and the red blocks is the second Gaussian. We have a buffer of parameters. We have a buffer of observables. I'm not listing the constants, and I'm not listing normalization factors. Those could be used, but they're not used in this example. First, when we configure our PDFs, we have two parameters that we're going to be passing, and the arrows are pointing to those values. Next, we have our parameter that we're going to pass, and these two PDFs we're sharing the first parameter value. So if you look, P1 looks up in the blue, which is the first Gaussian. You have an index of 0. We look up that value in the parameters buffer, and that value is 0.01. The second parameter that is only used in the first Gaussian is an index of 1. So we look up the index, which is going to be 1, and that is the value 0.05 from the parameters. And then we have the third one, which is the sigma for the Gaussian PDF. Index is 2, and then we look that up, and that is a 1.1. We also have observable values that we need to track, and we have indexes for these as well. So the first one is 0.1, and the red one is 0.5. So using this information, what we really want to do is we want to reduce the amount of memory accesses that we have. So we have 4 separate arrays that we're using. In this case, we're going to use a floating point constant buffer and cast it appropriately if we need any integers. And this also does require a pre-pass step, but from the user's perspective, they don't have to make any different calls. Everything is handled underneath the hood. And this is the new layout of what we're after. So we have our observable indexes, we have our parameters, our constants, our normalization factors. The light blue is our first Gaussian, the red is our second Gaussian. The one thing to note is that we are, this is a trade-off. We're adding extra memory in order to reduce randomized memory accesses. So the 0.01 is duplicated in the second Gaussian. We have another 0.01. So look at this. So that example doesn't really make any sense. So let's look at a real example of using two Gaussians. So we're going to add both of these up. The way this is structured is that you're going to pass in your add PDF, and you have two components. You have two Gaussian components. The way this is going to lay out in memory is that you have your red add PDF. You're going to populate all of your observables that you're going to use in this little red box, and then you have your green box and your purple box. And you're going to do that for the parameters, the constants, the normalization factors. The goal with this is to reduce the amount of random memory accesses and also to reduce the amount of memory accesses. And in addition to this, it makes it a lot easier to develop. You have a pretty straightforward model. You don't have to track indices around. It's pretty straightforward. So the performance, the graph at the top is showing you OpenMP performance and comparing version 2.0 with version 2.2. The graph on the bottom shows you the GPU version, 2.0 version, and 2.2 version. And the two main things I want to point out is that the CPU performance went down drastically with these indexing changes. However, the GPU performance, which is what the goal was, did increase. So if you know what your target hardware is, it's best to target memory layouts specific to that hardware. So now I want to shift gears a little bit and talk about how we create this new PDF using C++. We have three main components. We have a constructor, we have this recursive set indices, and then we have our device function. And I use quotes around device function because device in this context is specific to CUDA, but we use it as more a working function. This is the function that does all the work. For our constructor, we are going to track locally to the PDF our parameters that we're going to use, our observables, and our constants. We're going to register them. So we have register parameter, constant, and observable that we'll call. And when we are done, we're going to initialize at the very bottom of the constructor. Here is an example of what a constructor would look like with this new format. We have an observable. Our observable gets registered using GUPDF. And then we have two parameters. We're going to register our mean and our sigma. IDX and IDX1 and IDX2, those values I'm going to point out later, but those values are going to be 0 and 1 respectively for how they were added. Next is recursive set indices. So what we need to do is we need to copy locally our internal PDF into a global, temporary global structure that's going to be used later. So what we have to do is we have to copy everything from the observables, from the constants, the parameters, and copy them into this buffer. We also need to do this for all of the components for the PDF. And once we are complete with that, we're going to copy this over to the GPU. And here is how this is going to look. Key thing to take away is that we have this pointer to Gaussian. That is a device function. We still have this functions that we need to track. And then we also have a populate arrays. This is the helper function that you can call that will do all this copying for you. Before diving into the device function, the parameter container is the access method for accessing all of these local PDF values. And this is beneficial because we can hide all of the implementation details as well. If there is going to be better performance doing something differently, the user won't have to change their code. It'll be handled underneath. We also have two increment functions that we need to do. The first one is a fast method, and if possible, you should always use it. You need to increment by the number of functions, parameters, and constants. The second version is the slow version, where you have to look up those values in order to increment. And I had mentioned before about the constructor indexes. Those are going to be the same as the device indexes. So on this next slide, you'll see the observable. You'll see the parameters. I call get parameter and pass it as 0. So that ID, when I registered it initially, will be the same ID that I'm going to use here, which will make for debugging a lot easier. We don't have to have this double lookup to make sure that the values are the same. And then at the bottom, we also have this PC increment index. And the first parameter is our number of functions. Then we have our number of parameters, a number of constants, and then observables, and our normalization factors. We need to call this when we are done fetching all the memory that we're going to use for our device function, and then we can tell the parameter container that everything is up to date. And then it gets ready for the next function that's going to be called. So for the future, some other potential performance improvements that we have discussed has been changing observable data access to be a structure of arrays as well. There are definitely some difficulties with this, but this is something we're looking into. Also, in addition, the way the thrust creates these kernels is another area for improvement where we can reduce the amount of registers that are used, and that will improve the performance. So in conclusion, using multiple GPUs, having a large amount of events, 1 GPU, 4 workstations, we can get pretty much a 4x speed up. With memory optimizations, changing only the caching from array of structures to structure of arrays, we got a 25% increase. Utilizing the read-only cache, we got a 20% improvement. And utilizing the new indexing scheme, we got a 32% improvement. The new PDF creation that will be available in 2.2, this is going to help with readability and debugging. And it does have a performance degradation for OpenMP, but this is something that we can look through and profile it. And really, if I had one thing that if you take away from this talk at all, it's that the memory layout matters. It's very important, and hopefully these numbers will convince you of that. So if there are any questions, please go ahead.
Thanks very much, Brad. So, any questions from the room, maybe? I can ask one question, general, maybe for any of you three. Do you have a vision for Goofy 3? You haven't mentioned Goofy 3.
I do have some ideas, but I don't have time to work on them. But
it's called the vision.
Yeah. There's some, I think, some changes into the core that need to happen. I think maybe looking at building this on top of Hydra would be something that would count for Goofy 3. We could potentially get a nice performance boost from that, in theory at least. So far it's been iterative. We're still in an iterative process, and I think right now I'm hoping that people will be using this and giving us feedback, because I think that's something we really need to go forward.
That makes sense. Okay. Any questions or comments from outside?
So this is Peter. Do you have a sense of how big your sort of user base is at the moment? Do you get statistics? It's a general question for all of you.
It's small. There's been one group from CMS in Bari who's used this fairly extensively. And within LHCb, there have been of order 4 analyses either done or being done that are explicitly using GoofIt. And 1 Babar published.
So in terms of the relative capabilities of GoofIt and RoofIt, in terms of just pluggable, other than actually building things, on top of one or the other. Are there any, besides the technical advantages of speed and things like this, are there any, what would prevent someone right now from using GoofIt if they have something implemented on RoofIt?
So there are two possibilities. One is that they have an underlying PDF which is not yet implemented in the GoofIt C++. And the other is that I think RoofIt has a lot of ancillary tools which do not exist in GoofIt. Things for plotting, for example, which is not built into GoofIt, where the GoofIt users have traditionally used GoofIt plus root to do all their plotting, for example. Although with the new Python bindings, it may be very, very easy for people to mix GoofIt and say matplotlib instead. It's certainly not as mature or complete a project. The focus has really been on the fitting.
So the question is there another, are you at the point where I get the impression you're at the point where adding additional users is interesting, right?
Absolutely.
So the question is whether there's another strategy here to make it more visible to people. I think we should think about that.
Agreed.
Okay. And so, other than just your knowledge of the fact that those groups, Alexis and the groups in LHCP and a bar are using this, you get statistics from the downloads.
I don't have exact statistics, at least on the on GoofIt, though. There's definitely some activity, and I've occasionally gotten messages from people like on the issues page where somebody needed a different type of convolution, and then they were able to implement it, and actually they were never able to get permission from their collaboration to give me the code for that. But I'm not completely sure what they were working on. They kind of disappeared after that.
Yeah, so sometimes happens. Okay. Okay. So that's my question. So where we sit community-wise.
So Jim Bavarsky has some comments in the chat window. He says, if I had a working microphone, I would say that you right now have a Pandas GoofIt fitter. It could be used by data scientists beyond HEP. It's also value add to non-HEP data analysis because most fields haven't gone as far into the explicit ansatz style of statistical inferences as HEP. I'm not quite sure what that last part means.
The one person I spoke to, actually, I believe was not in HEP. I think he was in, I'm not completely sure, but I don't think he was in a HEP experiment. I think it might have been astronomy or something else.
You do have a main list where you can get feedback and things, right? So
there was
in principle, you can request some kind of statistics.
Yeah. The best place right now is still the GitHub issues, things like that. If
you can see the activity.
Mm-hmm.
Jim may be right. Maybe there's an opportunity here to advertise this in some other completely different forum, right? And it's non-HEP, and see if you can generate a bit of a user base there that may even be interested eventually in developing pieces, or maybe sort of push it in new directions, even relevant for HEP.
Message taken. Yeah. Okay. I think He's taking the care. Okay. Anything else from outside? I think from here, from the room, I don't see any hands anymore. So yeah, if nothing else, then we can close the meeting. Thanks so much, everybody, for joining. Thanks to all three speakers as well. See you next time then.
Thanks, bye.
Was good, bye.
Thanks very much to all the speakers.
I'll have to figure this out.